Okay, for those of you who were gone, we had started limiting reactants and percent yield. And, well, not percent yield. We're going to do perhaps one or two problems of that today. So for those of you who were here, are we comfortable with limiting reactants? So why is it so important to determine what the limiting reactant is? Not because, oh, well, that's what the question asks for. What is the limiting reactant really determine? We said it yesterday. Well, in other words, how much product you're going to form. So before parts of this was erased, as you can tell, we calculated this to be the limiting reactant. We do not want to calculate how much water or how much nitrogen is going to be produced off of our excess reactant. It's not going to give you a clear and concise answer. So that's why you want to find the limiting reactant. Okay, so if you choose, go ahead and turn to page, let's see here, approximately. Okay, approximately page 315. 315. Okay. Do you feel you need to do another limiting reactant problem? Let me ask you that. No? Okay. I thought I heard no. Well, we will, yeah. All right, fair enough. Okay, so on page 315, okay, which would you prefer, number 1 or number 2? Okay, so what we see happening, it says carbon reacts with steam, okay, in the form of water, all right, at high temperatures to produce hydrogen and carbon monoxide. So again, remember one of the aspects that we had said back in chapter 8, all right, not every problem gives you the balanced chemical reaction. Here's another case for that. So it's talking about this, okay. We don't want to learn about salts, do we? Carboxylate salts. You think we know why they're so important? Well, maybe some of the vitamins that you need to take in, they're not water soluble. But when you react it with a base, you form a carboxylate salt, which then makes that substance then soluble to mix into the blood so it can be moved from point A, wherever that is, to point B. Okay? It just okay, so with number 2 on page 315, carbon. What are we starting with? So what do we have as byproducts? We got hydrogen, right? Okay, now, it doesn't tell you what, okay, I'll go by with what you said. Okay, so we're not nitpicking here, okay? One of the things, should you write this, anything you do beyond that is what? Is wrong, okay? And that's human nature. We're human. We're going to make mistakes. That's just how we grow. I think you would agree, okay? So carbon monoxide plus what? Okay, there again, if we don't do this, remember that hydrogen is diatomic. You're going to make a mistake there too. All right. It does not. So what's significant about that reaction? Is it balanced or not balanced? It is balanced. Okay? So that's how we get it started. Now, that's not all the information that we have. We see in part A 2.4 moles of carbon. Okay? So we got 2.4 moles. 2.40 moles of this in what? 3.10 mole of water. Okay, so steam reacts to give us these two byproducts. Now, the reason that I would suggest that in any problem that is assigned to you, write this down above here. So for those of you who were here yesterday, notice we did the same thing. Why is writing this above here a good idea? True. But what does it tell you about your carbon? It tells you you have 2.4, okay? So rather than having to look back at the problem every time, if you write it above there, it tells us you can think of it as currency. You have $2.40 of carbon and $3.10 of steam or water. And it tells you, well, what's the limiting reactant between those two, okay? So I would suggest you just don't look at that and try to analyze, well, we convert one to the other. It does look to me like what's going to happen is carbon is possibly the limiting reactant there. I just tried to glance at it quick, and it was just a guess. And I was right. Carbon is your limiting reactant. Okay, see? See how easy that was? Well, do you suppose carbon is our limiting reactant because it appears we have less of it? No. What is it that, what board game did we talk about yesterday? Battleship. Okay? So what happens is kind of picture these two substances are playing battleship. So this fires at water to see how much is required. So this fires back at carbon to see how much is required. Okay? So what's significant about the mole? It's just a what type of unit? It's just a counting unit. That's all it is. All right, so, or the amount of, you could say the amount of that substance. I mean, that's probably a better way of looking at it. So 2.40 moles. And I would suggest that you don't do this either. Even when we look back at our equation, do we have any coefficients? No, because nothing changed. There's a 1 in front of each one of these. So what I'm getting at is I would suggest that you do not just write the problem like that. What, in your estimation, what is missing? Say that again. The labeling. Because we got 2.40 moles of carbon. So we want to put that there. So for every mole of carbon, we get 1 mole of what? Okay? So notice a mole to mole ratio, but nothing's changed. We have a 1 in front of each one of those. So we need 2.40 mole of water. And what did we write above that? 3 letters. REQ are required. Okay? So we need $2.40 of water. How much water do we start with? $3.10. So do we have enough water? Yes. Said don't just guess at these. Some of you may be able to look at that and say, well, yeah, I know it's going to be carbon, because when we take the 3.10 moles of H2O and multiply that by 1, and we need 3.1 moles of carbon, but we only have $2.40. Now, we said that really fast. How many of you would actually follow that logic? Okay? Are we on the bus here? You two are on the bus? You two on the bus. Okay, and fair enough. It's better to be honest, okay? Because how can we help you if we say, well, we got it when we actually don't, okay? And I think that would be a fair way to look at it. Okay, so we know how much water is required. Yes? We haven't got that far yet. It is. But we haven't answered the question yet. Okay? So now we took this, fired a shot at water to see how much is required. Water is going to fire back at carbon to see how much is required. So 3.10 mole of water. We cancel that out by saying for every mole of water, we get a mole of carbon. So 3.10, by taking 3.10 times 1 divided by 1, just going to get the same answer. Now, are we going pretty fast? Well, yes, but this is nothing new from all the way back in chapter 3. I think we would agree, correct? Okay. So, again, we would write REQ. Okay. So, we need 3.1 or $3.10 of carbon. Well, how much did we have to start with? 2.4. So, do we have enough carbon? No. That's going to limit what we can actually produce on the right-hand side. Okay, so now what we can do is make our basketball analogy. So who can we pick on? And there's 5. Okay? You're the cheerleader. Wasn't that impressive?
Oh, yeah.
Okay. Okay, so we said 1, you volunteered, then you said over here, that was 4, then we said here's 5. There's our starting 5.
Oh, yeah.
I'm the coach, there's our cheerleader. Okay? So, when we're calculating this limiting reactant, what did we say yesterday? The team that is behind in basketball is probably going to say, we should go after this person. Why? The weakest link or the worst free throw shooter. Okay? So, 1, 2, 3, 4, 5. Of you 5, who is the worst free throw shooter? Okay? Now, that has happened when a former school I used to work at, I had kept the book for them as well, and upon doing so, there's at times in certain games where uh, the coach is saying, okay, who shot the least amount of free throws? Okay? Or who hasn't shot yet, or something to that effect. What he's doing is looking at who he can foul, okay, to try to get that ball back. So in the same sense, carbon here is the weakest link, kind of like that of the worst free throw shooter, because that carbon is going to limit how much of this is going to be produced. Okay. So water is the better free throw shooter. Okay. And remember, we cannot base our, let's say, assumption or logic in saying, well, it has to be carbon because we started with less. Okay? Don't do that. Okay? To me, it's like memorizing formulas. Don't memorize formulas. Don't memorize the periodic table. It's better to know how to use that than to memorize it. I think you would agree, correct? Because that's what we were talking about in physical science today. Okay? So, for instance, those little red numbers along that left-hand column, what are they? They're periods. Why are periods important in Bohr models? Yes, the energy levels. I like shields better. We know what you meant. That's technically that's right. Yeah, it's how many shields there are. But all set aside. Okay. So, like I said, it's so much more important to know how to use that than to memorize. Now, some of you probably do have it memorized. In other words, as we're looking at that clock, we could say, well, it's hydrogen scandium right now. No, 121. What's element 21? Is it scandium? Okay. Yeah. How many? There are clocks that you can buy that has, one says hydrogen, 2 says helium. So are we following along? 3 says lithium without looking. 4 is beryllium. 5 is what? Starts with a B. Boron. Then 6. 7 is nitrogen. Oxygen. 8. You're flunking. Fluorine. That's 9. 10 is neon. And then we're going to say Na for 11. Sodium. And then 12 is Manganese? No, magnesium. Yes. Someone said manganese, I thought. Okay. Okay. All right. So that is part A. So part B, how many moles of each product are formed? So, when you do this, okay, you've made this determination, just like what did we see in this equation yesterday that we did that we have not done here yet? No. It's in the equation. There's something that the first equation has in purple that we wrote, and the second equation is written in green, but we have not wrote these 2 letters yet. LR. Why are we, you're correct, why are we writing LR? People could get confused with which one is... Yeah, because water is your excess reactant. Okay? So, see how we wrote limiting reactant. Let's do the same thing. I don't care where you do it. Write it here, down here, to the left, whatever. Limiting reactant is carbon. So, what we see happening is not going to have such a big deal on the amount of moles, but it might on the mass. Okay? And also look at what you're starting with. Now, this is another, it's just human nature. When people are looking at all these problems, they're going to look at this and say, oh, well, I need to see how much is being formed on this side. And then, well, our carbon is our limiting reactant. And then they look at this and say, well, I got 3.1 moles. Is that correct? The answer is no. Why is it not this number? That's what's required. We need to do or start with what we have, not with what we need. Okay, so as we look at this then, since we're starting with 2.4 moles and nothing's changing, 2.4 times 1 is just 2.4. So one way to look at that would be saying this here. Remember, we're starting with what we have, not with what we need. I don't know why I erased that. So moles of, we'll just say carbon monoxide. Okay, so now we got our two products over here. Remember we said it's 2.4 for both of them. 2.4 times 1, 2.4. 2.4 times 1, 2.4. So that's how much of each product is formed. It doesn't say grams, otherwise there would be just one more step onto there. And then finally step C. Now it says what mass of each product is formed. See, I get to cheat again. And I can write 4.85 for, was it hydrogen, I think? Yes, for H2. And then 67.2 for carbon monoxide. Now, do you suppose we're just pulling them numbers out of the air? Well, kind of. But we can erase these, okay? And now that we're in moles of carbon monoxide, how do we get rid of that? For every mole of carbon monoxide, we get what? Saying the mass of each product. So how many grams of carbon monoxide are there? Is that right? I think my math is correct. Sure? Okay. Close enough? Okay. I'm a barium. What's the symbol for barium? I'm a barium. What did I just do? Pulled the pin. Yeah, you said it was close enough. So we throwing grenades here? Must be because I'm a barium. Good one, wasn't it? Okay, so if we take 2.4 times 28, 2.40 times 28.02, what a coinkydink, 67.2. Just like what we said. So I'll leave that up to you if you really need to see what you get for hydrogen. Well, all you're doing is taking 2.02. Human nature. What happens if we just do this? Why is that wrong? Because yes, keep carrying that 2 so you don't forget to multiply that by 2. Okay, so 2.02 times 2.4. What coinkydink? 4.848, rounded up to 4.85. Just like what we wrote down. Okay? All right. So, are we comfortable with limiting reactants? The only difference is you four have had one more day of experience. For whoever missed, you can go back and see what we did in class yesterday. But that's your responsibility. Okay, so one of the things you need to get this through your head, what percent yield means. Okay, so what percent yield means is this, PY, or percent yield. Okay, so Jordan, you're on the free throw line. How many free throws, now we're not saying last night, but on a night, how many free throws did you shoot? Yes. Okay. You shot 4 free throws. Of those 4, how many did you make? Okay? So what happens when you get a fraction? You can change that to a what? Yeah, that's how you get a percent yield. Okay? Now, what this means is you actually made 3. Okay? So theoretically, we're saying that you would make 4. What we do is in a reaction, the actual yield goes on top. Okay? And on pencil and paper, okay? Pencil and paper with what you calculate is what you theoretically come up with. Okay? What that means is there any machine that is 100% efficient? No. So just like with what you just answered, there is no percent yield that's going to give you 100%. So that's why I'm so happy you did not say 4. Pat yourself on the back. Okay? So what you're doing with percent yield is in the problem, it's telling you, for instance, you have made 780 grams of a substance. What is your percent yield? Well, on pencil and paper, you theoretically state what you would come up with. Okay? And that's what this means. We'll quickly go through and do a problem. And notice that when this is handed out, does it say that this is due tomorrow? That's Friday. What does it say about tomorrow? That means that time is yours. Wouldn't it make sense to use that efficiently? Yes, it would. See, you people are getting smarter already. Mm-hmm. Wasn't that goodly? Okay. All right. No, it's just barium. Takes all sorts. Yeah. I mean, yeah, I'm a barium. Yep. Do we believe that?
Oh yeah.
Okay. Yeah. Okay. Breathe, breathe, breathe. Okay. All right. So practice problem number 1. Holy cow. And I didn't even do my dinosaur interpretation. Are we okay over there? Okay. Just breathe. You never think of 56 the same way. That's barium. All right. Okay. So we'll set this problem up, and then we will finish it tomorrow. How's that? I wanted to give you a little bit of time to look at this and say, gosh, this stuff stinks. Maybe you will. Okay, so practice problem number 1 on page 318. It says methanol can be produced through the following reaction: carbon monoxide and hydrogen in the presence of a catalyst. Okay, so we have our carbon monoxide plus hydrogen. Notice they're nice enough to give you that that equation. They even balance it for you. So methanol, we wouldn't expect you to know what that means, but there's your methanol. Okay, so if you did not have to balance that, you would look at this, and sometimes it's easy to forget that when elements are split up in 2 separate spots, that we got 4 hydrogens, then we need to put a 2 here, okay, and then we see everything else is balanced. Okay, so what it says, if 75 grams of carbon monoxide, okay, this is another thing I would suggest that you do. It says if you have 75 grams of this, okay, 75 grams of carbon monoxide reacts to produce 68.4 grams of this. Okay? Goes on to say, what is the percent yield? So, of those, which one is the actual yield? Is it 75 or is it 68, do you think? It's this one, okay? Because this is what was actually produced in this reaction. So it's asking for the percent yield, or this one. The 68 goes up here. So how do we get the theoretical yield? On pencil and paper, you convert grams of this to what an X amount of grams that you theoretically should come up with. And there's your bottom number. Okay? We'll continue with that tomorrow. All right.